Okay, so what we're going to look at is we've been studying limits, and now we're going to look at one particular type of limit, and that is the limit of the difference quotient, which is the derivative. But now I need to back up a little bit and talk about the reasoning that we use with the derivative. And let me I'm going to need the calculator here in a minute. So let's suppose that we have a curve, and let me get the calculator open. I'll close it. Okay. Whoops. Okay. Okay. So let's just suppose we have a curve, some curve up here, maybe like this, and this is some function f of x. Okay, so we're just looking at this curve, and we're interested in the steepness of this curve. We're interested in, I'll just describe it that way at first. The steepness of this curve at this point x, just some random x. Now, what we could reason is this. We could say, well, I don't know how to get the steepness of that curve. However, I do know how to get the steepness or the, how fast a line is, what the slope of a line is between 2 points. So what I can do is I can say, well, I'm going to do that. So I can say, okay, I'll go over here a little ways, x plus delta x, where this part right here is delta x. Okay? So that's one way we can think about this, and we can say, okay, I know how to get the slope of a line, so what I'll do is I'll use that idea to kind of describe the steepness of this point right here on the graph. In other words, how steep is this? If I'm standing here, and I want to know, well, how steep is my climb going to be? I don't know, but I can know if there's a line going through there through another point, I can measure the steepness of that line, that incline. So here's what I'm going to do. I'm going to think about the slope of that line. So I'm going to do this. I'm going to get the slope. This right here is x plus delta x, and this is f of x plus delta x. Okay, that's what that point is, and of course this is just x f of x. Now, if I want the slope, what I'm going to do is I'm going to take the change in the y's over the change in the x's. And the change in the x's are x plus delta x minus x. Okay? Now, what this is we could call that the average rate of change. So we could say, okay, from x to x plus delta x, that's the average rate of change. Okay? That's what we could call that. And it's not a very good estimate because you can see it's a lot steeper there where this guy is standing. But if we go ahead and simplify this just a little bit, then what we have down here is just delta x. Okay, so now we have an average rate of change there. Now, like I say, it's not a very good estimate, so I don't think we would be content with that. So what we can do is we can say, well, let's use this line instead. We'll use that line. And that's a little better, right? In other words, I had x, and I still had x plus delta x, but I made the delta x smaller. So in other words, I moved these points closer together. And now the steepness of this line seems like it might be a little bit more in line with the steepness of the curve. Well, still, we're not content with that. So we can say, well, I'm going to move the lines, I'm going to move the points even closer together. Okay? And you can see every time I do this, it looks like I'm getting a little bit better representation. And then finally, we can say, well, let's make them really close together. Let's make them like that. Okay? Now here's what's going to happen. So you can see that the steepness of that line there is very much like the steepness of the curve. So it would make sense to us probably to go ahead and use that line, that purple one, rather than that red one over there, the slope of that one. So that's what we want to think about. Now, we see the game that we're playing here is we're just letting delta x get smaller and smaller. So what we might do is we want to say, well, I've studied limits, so let me just open up that can of limit and pour all over that thing. And if we do that, then we get this. We get delta x down there, and we're taking the limit as delta x goes to 0. And here's the terminology. Notice this red line, this right here, and all of these lines, these are secant lines. Okay, those are secant lines. Now, what this right here is the slope of the tangent. So this one right here is the slope of the tangent at x. Okay? So at this value right here, this is the slope of the tangent, because here we've got a line that touches this graph at that point, f of x. So f of x is a point on that curve, and it's also a point on this line that this is the slope of. Okay? So that's the slope of the tangent. Now, here's something else we call this. The slope of this tangent is also called the derivative of f at x. That's what it's called. Okay? And when you hear this derivative, you can think of it's a function and we derived it. Okay, so it's the derivative of this function at x. Now, if someone ever asks you what is a derivative, the correct answer is it's the limit of the difference quotient. Now, it does measure change, but that's just what we use it for. I mean, we use it to measure change, but it is the limit of the difference quotient. Now, you could also say it's the slope of the tangent. Okay, any questions about that? Now, the way we denote this is if it's the function f, we put an f up here with a little mark, and we call that f prime of x. F prime of x. That's the way that is referred to. Okay? F prime of x. Now, prime doesn't have anything to do with prime numbers. We just use, it depends on the context. Now, we could also, exactly the same thing is, we could say d dx, like that, of f of x. This is the derivative of f with respect to x. That's what that is. Okay? The derivative of this with respect to x. Now, you know that oftentimes we'll write y equals f of x. And we use this function notation, but sometimes we just say y. So we might say f of x equals x squared. Or we might say y equals x squared. So you could see this. You could say dy dx. And it's the derivative of y with respect to x. Okay? So we can take the derivative with respect to other things besides x, but this bottom here tells you what you're taking the derivative with respect to. Now, here's the thing about this notation, dy dx. That's pronounced dy dx. Usually, no one says dy over dx. They'll just say dy dx. When we say that, you have to remember the dy and the dx, really they don't have any numerical value. It's notation. That's what it is. But we're going to find that this behaves an awful lot like a fraction. And we're going to find that out next class period. We're going to work with what's called differentials. And we're going to find these behave an awful lot like a fraction. But for right now, we're just learning this notation. This is f prime of x. That's what that is. So these are the same thing. Okay? Any questions? So the derivative is the slope of the tangent. Now I want to look at a real example of this. So here we go. Let's look at an example, just so we can have something concrete. Let's suppose that we have this function f of x equals x squared. Okay? And I want to apply the difference quotient to this thing. In other words, here's what I want to do. I want to find the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. That's what I want to find. Well, so let's see here. F of x plus delta x, let's put that in. Okay, so that's going to be just x plus delta x squared, right? Minus f of x, well, that's just x squared over delta x. Okay, so see, now this right here is f plus delta, x plus delta x. That's what that is. This is f of x, and of course delta x, see? So in other words, what we have here, and let's just look at this a minute. Let's look at it graphically and see what we've got. We've got a nice x squared right there. And we've got this point over here, x f of x, which is x squared, right? That's what that is, okay? And then we've got this other point over here, which is x plus delta x, comma, x plus delta x squared, right? Does everybody see that? In other words, this is the point x f of x. This is the point x plus delta x, f of x plus delta x. And in this case, f of x is x squared. Okay, y'all see that? So if we're getting the slope of the tangent, it's this minus this, which is what we got right there, all over delta x. Change in y's over change in x. Rise over run. Okay. Now, let's see if we can do something with that. Now remember, when evaluating limits, the first thing we just try to plug in. So if I plug in a 0 for delta x, I get 0 over 0, which that's wrong. We shouldn't do that. So what we do, we say, oh, okay, let me see if I can simplify this. And it looks like probably the most straightforward way to simplify this is just multiply everything out, gather like terms, and see what happens. So if I FOIL this bad boy right here, this first one, I get x squared plus 2x delta x plus delta x squared minus x squared all over delta x. Now notice what I did, just to be sure you understand, I just took x plus delta x and squared it. And then I multiplied through. Okay? Okay. Now, when we do this, you'll notice this lovely thing happens. That cancels. Those cancel, okay? And now we're left with something that's a little bit simpler. Notice that I have a delta x ha und ha. So I'm going to factor that out. I'll just factor it out. Look at this, delta x. And then we just have 2x plus delta x. And a delta x down here. Now, this cancels. And now, we can plug in a 0 for delta x. If we plug in a 0 for delta x, all we're left with is 2. So look at what we have now. We have that f prime of x is equal to 2x. That's what that is. So that tells me the slope of the tangent at x is 2x. Okay? Does everybody see that? Now, so here's what we've just produced. We have a machine here. This is a machine. And its functioning, or its purpose is, you give me an x, and I'll spit out a slope of a tangent. That's what this is. Okay. Now the particular thing is it doubles it. You put in an x and it spits out a slope of the tangent. That's what that thing is. That's a machine that generates slopes of tangents. So let's find this. So the slope of the tangent at x equals, let's say 3. The slope of the tangent at x equals 3 is f prime of 3 equals 2 times 3, which is equal to 6. That's what the slope of that tangent is. So we use that to know how steep the graph is at that point. Okay. Now, here's what I want to do. Since we know the slope of the line, I want to go ahead and figure out the line, what the line is. I want to go ahead and find that tangent. Because remember, here, if x equals 3, then f of x is 9, right? So I've got a point and I've got a slope, right? I've got a point and a slope. This is the point and this is the slope. Now, when I have a point and a slope, so for example, if I'm given x naught, y naught, and I'm given a slope, I can say y minus y naught equals m x minus x naught. Remember, that's the formula for a line that we can use. That's one of the formulas, point-slope form. So if I know that, now, by the way, are there any questions about this? Oh, I just made that up. I was just looking for an example. I could have picked any number. Yeah. Okay. Any other questions? Okay, so let's write the equation here. We've got y minus 9 equals 6 times x minus 3. This is our equation for the tangent. Now, I want to show you something that's cool about this. If we go through here and we have 6x minus 18 plus 9, okay? So I just am kind of clearing this out. I get 6x minus 9, okay? Now, that's my equation for the tangent. Okay, now let's look at our calculator here. If I'm going to put in x squared in here. Okay, so here is x squared. And I'm going to put down here, what was it, 6x minus 9? Okay, there we go, 6x minus 9. And let me change my window. I'm going to go from 0 to, let's say, 15. And actually, I don't need to go from 0 to, yeah, let me do this. And let me go from 0 here to, let's say here, maybe 15 as well. Let's just do that. Okay, now now remember, we're looking for the tangent at 3. And let me not go to 15. I don't know what I was thinking here. Let's just go to like a 5. And then let's go to 4. And then this will be 16. Let's do that, 16. Okay, that's a better choice. Okay, now, there is my tangent and there is my curve. Now remember what we're looking at, now realize that that tangent and that curve share a point. The point they share is 3, 9. Now I want to zoom in a little bit. And before I zoom in, I'm just going to do a second calc and value, and I'll type in a 3 and enter. Now I'm going to start zooming in. So I'm going to zoom in to, here we go, zoom in right there at 3. Okay? Now, so what you see there is my tangent and you see my curve. So let's zoom in again here. There it goes. Look at that. Okay? Now, let me zoom in again. Heck, this is enjoyable. Now, you'll notice as I zoom in more and more and more, you can see why it's reasonable of me to use the slope of the tangent to talk about the steepness of the curve, because they don't look any different. Okay, so these two things look pretty much the same. Now, you know what? My video, I noticed something here with the people that are going to watch this video that aren't here today can't see this. Because look, here's where it cuts off. But they have to trust us, okay? Now, one thing I can do to help them, though, let me see here. Whoops. Let me cut this out for them. Whoops. Hang on. Okay, I'll cut this out for them so they can see it. Yeah, that will help them. Oh, I'm supposed to do that? Okay. Okay, now let me paste this. Whoops. Oh, let me just do this. Okay, there it goes. Now the people on the video can see it. There you go. Okay, so you can see that the tangent and the curve are pretty much the same. And now what we've done there is we found the derivative and we've written the equation for the tangent. Now, so let's just make some observations here very quickly before we go any further. So these are just some observations about the tangent. Now, you notice that, let's just look at a curve here. If you, and we're going to get more into this later, but notice that this curve is going up. If we go from left to right and we're climbing this, or we're walking on this curve, we're climbing here, right? We're climbing all the way up to there. And then over here, we're decreasing, right? We're going down, right? So this function is growing in value on this green, and it's decreasing in value. What is that, aqua or something like that color? So it's decreasing in value over there. You can see that. Now, if you think about tangents, so let's just think about tangents here. Let me draw some little tangents. You notice that whenever this curve is going up, whenever we're getting higher in value, our tangents have a positive slope, right? You can see that. Now, on the other hand, if the curve is decreasing, our tangents are negative, right? Or the slopes are negative, right? So that's one of the things we want to notice just right. We might as well right away that the steeper the graph, the higher in absolute value the tangent's going to be. It's going to be positive if your graph is going up. It's going to be negative if it's going down, right? So that's just some observations we need to make. So the tangent, measures the steepness of the curve. Now notice this, right up here at the top, at the highest point, the tangent is 0. The slope is 0. So that's something that's going to mean something to us in the near future. Okay, so when the graph is going up, the steeper the graph, the higher in absolute value the tangent, whether it's going down or up. But if it's going down, it's negative. If it's going up, it's positive. Okay, now, what we've done is we have found the derivative. We've used the definition of a derivative. Okay, so these are going to be some more examples. Okay, we've used the definition of a derivative to find the derivative for x squared. But what we want to do is we want to use that for other things too. So let's just let's fancy it up a little bit and say, well, let's suppose f of x equals x squared plus 3x plus 1. And we want to find the derivative of that. Well, it's going to be exactly the same method. What we're doing, we're going to learn shortcuts, but right now we're just learning this method. And remember, what you do is you replace all the x's with x plus delta x. Okay, so look, here is x plus delta x. F of x plus delta x minus f of x all over delta x. That's what that is. Okay, so this is the initial plugging into the formula. the derivative formula. That's what that is. Now, the next step is to simplify, and the way we simplify this is we multiply things out. Okay, so I multiply everything out, and it's going to be just like before. We have it. And immediately, you'll notice this good thing happens. Things cancel, which is nice because this thing is getting out of hand. Now, once all those things cancel, every term up top is going to have a delta x in it. And therefore, we can factor delta x out. Okay, so dig this. Here's delta x. Now I have 2x plus delta x plus 3 over delta x. All right? Then I'll let delta x go to 0, and we're left with a very lovely 2x plus 3. And there's our derivative. That's our slope-generating machine. You give me an x, I'll chunk it in there, and it will spit out a slope of a tangent. That's what that thing is. Where? Yeah, that should be a -1 there. Thank you. And don't let me forget your nerd buck on that one. I don't want to give it to you right now. I'll give it to you at the end. But don't let me forget. Say, where's my nerd buck? I worked hard. Yeah, remind me about that. Okay, any questions? Okay, now our observations. Okay, so we've got this type. Now, we could also have ones like this. We could say f of x equals x cubed. Now, if we have x cubed, then our difference quotient is going to require just a little more algebra. It's going to be x plus delta x cubed minus x cubed over delta x. Now, remember, last time we talked about the importance of remembering how you multiply out, like squared, cubed, and even the fourth. It's good to just have those in your knowledge pot where you can just pull those out. Well, so for example, this one, we would multiply this out, and remember it's 1, 3, 3, 1 are the coefficients. So this is x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed minus x cubed over delta x. And once again, bad boys cancel there. Factor out the delta x. And when you do that, what you're going to get is you're going to get a 3x squared. See, and I won't belabor that point. I know that y'all know, how to factor that out and all. But that would be the derivative. Okay? Does everybody see that? Because notice that delta x completely factors. Here you have 1 left, and here you have x squared. Delta x squared. Okay? Any questions? Okay, now, what we want to look at are some ones that might give us problems. So we know how to do these. We know how to do binomials, basically. Difference quotient that involves the binomial. Now what we want to look at is one like this. Let's suppose that we have 1 over x. So now our difference quotient looks like this. 1 over x plus delta x minus 1 over x delta x. See? So now putting in for x, we get x plus delta x. Okay? Now, this is exactly what we did before, and on your test coming up, you'll have one like this, where I have to simplify that. Now, the way I simplify that is I multiply by the least common denominator, right? So, in other words, I'm going to multiply by x times x plus delta x here, here, 1 here. Look at that. All those x plus delta x's. And that's okay because it's like I multiplied by 1. X times x plus delta x over x times x plus delta x. And then I distribute it. Now, here's what happens. This cancels, and now maybe we have something that we can deal with. So let's see here. We've got the limit as delta x goes to 0, and then up top we have x minus x plus delta x. Now remember, you got to really watch your bad self, because if you are not careful, you'll forget the minus there, right? See, there's a minus there. Now let's see what happens. Got the limit as delta x goes to 0, and this is just going to be negative delta x. Like that. Because the x's cancel. Then let me go ahead and now if I let delta x go to 0, what I get is negative 1 over x times x, or negative 1 over x squared. Now this is the trick for simplifying the difference quotient if you've got end up with a complex fraction like this one. That's the trick. Now, there's one more thing I want to say about this, and then we can just do a few practice. But I hate to talk this long, but I want to get us to a good stopping place and have one compact video for the people that aren't here today. So let's look at one more type that we'll have to battle. Let's suppose that we have f of x equals the square root of x. Well, in this one, we end up with a difference quotient that looks a little something like this. Okay, so x plus delta x. Okay, see? So there's the difference quotient. Right there. Okay. Now, remember, we multiply by the conjugate. Okay? And the conjugate being, in this case, it's going to be the square root of x plus delta x plus the square root of x. So I'll do that on the top and the bottom. And the reason we do that is because when you multiply a times b times a minus b, you get a squared minus b squared. So if you've got radicals, you just lose them. And here's what happens because you're squaring them. And, you know, squaring is the enemy of the square root. So now here's what we get. We get x plus delta x minus x. Ooh, that's easy. Now the bottom, delta x times that whole conjugate thing. Okay, so this is the trick. Now, at this point, it's over. I mean, it's very simple what's going to happen next, because you can see up top the x's cancel. You're just left with a nice delta x, a delta x down here, and then this conjugate stuff. Okay, bang. Now delta x goes to 0, and I get 1 over the square root of x plus the square root of x. And a lot of times down here in Arkansas, we'll call that 2 square roots of x. We shorten it up. Okay? Any questions about that? Okay. Now, remember, we're going to learn shortcuts for this. Okay? So what we're going to do is we're going to get a little bit of practice using the difference quotient, just so we understand. And then we're going to refer to the difference quotient a lot. We'll always go back and say, okay, this is what a derivative is. Because what we want to do is we want to develop some shortcuts. And to develop those shortcuts, we need to be able to show that using the difference quotient, you get the proper thing every time. So for example, we want to figure out, well, what is the derivative of sine of x? Well, we're going to put sine of x, apply it to this difference quotient, and see if there's a general way, you know, is there something general that always happens when we run it through the difference quotient? So that's what we want to do. Okay.